I want to tell you a little bit about some work we have done with UAVs, and I looked a little bit at what the Payless project is doing, and this is very much relevant to what I'm going to say this afternoon, and it's also quite complementary to the presentation that you heard this morning from Lakeside Labs. So in the presentation this morning from Lakeside, the emphasis was on the use cases, experiments, and trying to understand to some extent what existing technologies can do to assist those UAV use cases and whether they can deliver the needed performance or not. So they presented some very interesting experimental results on this aspect. This talk is different. So of course, there's the common aspect is the fact I'm also talking about drones. Communication is definitely one aspect, and I also have an emphasis on experiments, but of a different kind. So if I need to clarify in just a second, I would say that my experiments, the experiments I'm going to present today are much more related to the robot side of things and not as much on the networking side of things. So that's why I say it's complementary. This is some joint work with Omid and Rajiv that are currently working in the lab, and former student Janting, and also with Obashi Mitra at USC. Okay. So the premise of the talk is a bit similar to the presentation this morning, which is that there's a need for this highly flexible deployment of networks. And in one of the cases that came about recently is following a disaster in the Puerto Rico island. If you remember, Google sent some balloons there to provide connectivity to people on the ground as a first kind of help. And this was quite successful, but there are some issues with those balloons. I mean, these balloons fly quite high up in the air, and the footprint is extremely large. So they indeed can give basic connectivity to a very large number of people over a very large area, but the data rates are not very high. And the other problem is that the balloon itself is not much controllable. I mean, it's basically controlled through the wind. So the idea was to see if we could design algorithms and prototypes for micro robots, similar to what has been shown this morning. So like quadcopter kind of robots that could be used to deliver more like a surgical help, not in the medical sense, but in the networking sense of it. That means providing help on networks exactly when and where it is needed. And that implies having a much greater level of control over the robot itself, and also being able to manipulate the trajectory or to come up with algorithms by which the robot is autonomous but can deliver a trajectory that is meaningful for the final mission. So the use cases that we consider is again similar to what has been presented, things like covering hotspot scenarios, sports events where you have suddenly a large crowd that overwhelm the capabilities of the local infrastructure, or sometimes disaster recovery where there's no longer any infrastructure going on. Another use case is IoT for various applications like smart cities, smart agriculture, and so on. And the last one, which I'm showing at the bottom here, is sort of peer-to-peer connectivity. So where the drone is used as a relay between pairs of users on the ground, which could be cars or which could be people like law enforcement or fire brigades in a search and in a rescue situation. I guess one big difference between some of these scenarios and other ones is whether you need an infrastructure in the landscape or not. So, for example, if you're doing range extension, the idea is that the drone is acting as a relay. So you need to have a base station not too far away that the drone is going to act as relay on. While in some cases for IoT data harvesting, you don't actually need a base station. The base station is represented by the drone itself. And the name of the game is to collect as much data as quickly as possible from the IoT network, which the drone will capture and will store locally before moving on to its base. All right, so let's keep in mind these differences, whether you're doing serving in a relay situation or whether you're serving as a flying base station situation. Okay, so today I'll talk about the main idea, which is, by the way, what is the number one reason why you want to put radio equipment on a drone? I think the only reason I can imagine is because the drone can freely move in 3 dimensions. That's the big advantage over fixed infrastructure. And as soon as you say that, well, it means that the number one challenge is where should you put the drone, or where should the drone go? So this is a problem of placement. And soon enough, if you want to design a real robot, you realize that you can't really use the statistical models that maybe some of you have seen in the literature. Of course, if you use statistical models, and by models I mean propagation channel models typically, you can do analysis. You can try to predict how useful is a drone going to be if you place it in a network as a relay or as a flying base station. But that's just going to be an average performance analysis. It's not going to be something you can implement in an actual robot on the field. An actual robot absolutely needs to be aware of its immediate surroundings to be able to react very quickly to what's going on around the robot. And that involves a fair amount of prediction and also mapping. Mapping becomes hugely important in that context. So I will talk about prediction, I will talk about mapping, and then I will talk about how you can do path planning once you have this kind of information in your hands. And then the last part of this lecture, I will talk about a very interesting twist to the original problem of path planning. When I say path planning, I mean planning the path of a flying robot so that it is as useful as possible in a network. The twist you can bring on that is knowing that to optimize the path, you really need to learn about the environment. You need to make measurements and use machine learning. What is the most efficient way to collect the data you need to learn? And that's the problem of active learning. That is also a very nice open problem in itself that I will talk about at the end. Okay, so there's all kinds of interesting problems that people talk about when talking about UAV placement. I think I mentioned the fundamental distinction that there is between a probabilistic placement and an actual real-time placement of a robot in order to provide guarantees of performance. But you have other forms of choices that you have to make. First of all, are you looking for a single static position for your robot, or are you looking at a path? Are you looking at learning everything you need to learn while flying, or is there a way to do a little bit of offline learning as well in order to kind of expedite the optimization on the day you have to complete the mission? Are you serving a large population of users, or are you serving maybe a single user? For example, in this morning, there was a use case about search and rescue. So you want to identify, a single user. Well, that's not the same as trying to serve or localize a population of users. So this is something very important to keep in mind. Another important idea is how you deal with the classical robotics and navigation problems that still exist, by the way, when you're talking about UAV and wireless networks. Well, you're still dealing with a robot that needs to navigate around obstacles and avoid crashes and so on. So there's all kinds of important control problems there that should not be ignored, but there's a way to probably abstract this out in the first phase. For example, if you predict that an optimal path for your networking mission from A to B goes a certain way, you can always program this path in the robot, and then the robot will, as much as possible, follow that path, while still trying to avoid obstacles that could exist along the way. So you can always combine with classical obstacle avoidance algorithms that are usually available off the shelf. So this is why I'm not going to talk about obstacle avoidance here. Okay, so as I said, if the goal is to ask the following question: where should the robot be as useful as possible in a wireless network, no matter what scenario or use case you're talking about? The number one problem becomes, well, it depends on where the communication is good and when it's not good. So it means you need to be able to predict in advance where the SNR or SINR is going to be good or not good. And that means you need to do channel prediction before the robot is actually flying there. So how can you do this? Well, as I said, if you're dealing with a real robotic implementation, it will be hard to escape from the concept of mapping. The robot needs to construct a map of its environment in order to navigate properly in it. So there are different kinds of maps we're talking about. For example, having a building map of the environment could be quite important, like the position of the buildings, the height of the buildings, the streets, and so on. But a radio map could be also very useful. A radio map is what you see on the right-hand side here. I don't know if you see the mouse when I'm moving it. But basically, this is a 2D or possibly a 3D map that predicts what the SNR or SINR is going to be at different places where you can put the robot. If you don't do that, if you don't want to use maps, then you have to use a probabilistic model. A probabilistic model is something that looks like this. There's some very, let's say, popular ones in the literature. For example, you have a probabilistic model that predicts the likelihood of having a line of sight connection between the robot and a ground user as a function of the angle that describes the path between the drone and the user. So if the angle is close to 90 degrees, then you have a high chance of maintaining line of sight. If it's close to 0 degrees, you have almost no chance of guaranteeing line of sight. And then you have other parameters like A and B that can be learned by making a lot of measurements. So the advantage of such a model is that it's very simple to use. It's, as you can see, this is a continuous function, which you can easily plug into a path optimization problem. And then you will get most likely a problem that can be solved using standard optimization. I mean, it might not be convex, but at least it's going to be optimizable using classical tools. So this is the big advantage. The main disadvantage is that this is okay to write papers, but to deliver an actual solution is not okay. And it's not okay because if you plug this formula into a path and navigation algorithm and the robots arrives at destination, maybe you'll realize at destination that actually that particular place is surrounded by tall obstacles and that the fading is very bad and that the channel is actually very bad at that place. And then you have to go around and then look for another solution. So this is why probabilistic modeling is useful in some contexts, but not necessarily in all the contexts. Okay, so the main thing about these maps is that there are two problems. First of all, why they are very useful. Well, they are not necessarily available, so you have to reconstruct this map. So this is the idea of map reconstruction. Usually what you have is a small set of initial measurements taken by the robots. So essentially, it will give you a few pixels from that image, and you need to reconstruct the rest of the image. So that's the reconstruction problem. The second problem that we are dealing with here is the fact that even if you manage to reconstruct the entire map, this information is extremely rich. And in fact, can be too rich. If you look at this particular map example, you see that it has a highly irregular shape, completely non-convex, which means that if you plug this information into a path optimization algorithm, while on the one hand, the map gives you all the information that you need, on the other hand, the optimization algorithm that you have to handle will not, anyway, it's going to be extremely complex. It doesn't lend itself to classical optimization tools. So you see, you have the trade-off between simple models that are probabilistic in nature, but not realistic, or very realistic models coming from maps, but not easy to handle mathematically speaking. So one interesting question is how you reconcile those two views and come up with good solutions. This is something I will talk about. Okay, let's talk about a little bit about the channel models that we use here. First of all, when you're talking about optimizing a path, you forget about fast fading. You're not at the time scale where you have to deal with fast fading. You're really only dealing with macroscopic fading, like shadowing and path loss. That's what you need to take care of. The second aspect, of course, that is very important is whether the link is in line of sight or non-line of sight. Okay, so this is again something that needs to keep in mind because the path loss difference between line of sight and non-line of sight linking is so huge that you better be able to predict at what places the robot will be in line of sight to its target user and places where it won't be in line of sight. Okay, so the way you do that is that you use a channel model. This is a classical, what is called segmented channel model, where you see that this is the received signal power, gamma, and then there is something here that depends on an exponential function of the distance. This is very classical. You have here alpha is a path loss exponent, beta is some sort of fixed offset, and epsilon is some kind of noise or shadowing, random variable. And then you have here, what is interesting, the subscript S. S indicates the class of channel you're dealing with here. So if you're far away from your target user, then probably you are in non-line of sight. If you move a little bit closer here, you may be in some kind of intermediate, lightly obstructed non-line of sight, maybe due to trees or something like that. And then at some point, if you fly close enough above the target user, there's one point where you can show you will enter line of sight and you will stay there. It's actually an interesting property. Is a nested property for these channel model classes. So D1 is a region that is nested inside D2, which itself is nested inside D3. You can actually exploit this nested property, but I won't have time to explain this today. Anyway, so S can have at minimum, let's say, 2 classes, line of sight, non-line of sight, but you can actually inject more classes to be a bit more realistic. Of course, if you put more classes, well, you're going to have to deal with a classification problem that is a bit more complicated. When you make your measurements, you would have to classify your measurements between one of these classes. And the more classes you have, the more easily you will confuse your machine learning algorithm. All right. So this is the overall picture. The robot is going to collect measurements using an initial flight, let's say. We call it sparse training because you cannot make measurements at all points of space. So you get measurements at some points of space. Based on that, you will try to do some kind of reconstruction of your environment, which could be reconstructing the radio map. But I will mention it could also mean that you're reconstructing the physical map. That's also possible because the two are tightly related through the channel model I have just explained. Once you have reconstructed your map, now you can move on to the path planning problem. Okay, and once you have decided what is your good path, well, you use an off-the-shelf navigation algorithm to take you there. So this last box I'm not going to touch upon. The whole thing can be online, it can be offline. So what is exactly the definition here of online, offline in this talk? Well, it has very much to do with the amount of information, prior information that the robot has before liftoff. If the robot takes off with absolutely no prior information about anything, for example, it doesn't know, or it will know at least the mission it has to accomplish. Like, is it a relay mission? Is it a localization mission? Is it a search and rescue mission? Is it, I don't know, peer-to-peer connectivity mission, etc. So that it knows. But it might not know the number of users. Where are the users? It might not know the channel model, or maybe it knows the channel model, but it does not know the coefficients, this alpha and beta, of these various classes of propagation. There's a ton of things that potentially you need to learn while flying. So if you have to learn all of that while flying, we will say it's a purely online scenario. If some of these can be assumed to be known in advance, then it will be partially offline, because there's that much less that you have to learn while flying. For example, typically in some cases, you may access some 3D maps of your environment just by looking at some websites, and you can inject that into the robot before liftoff. So that can be actually very helpful. So this is how I categorize online versus offline. Okay, this is an example of map reconstruction. You see the radio map that indicates, in this case, is a level of signal to noise ratio at various places, fixed altitude in the network. And then the crosses are examples of training data sets. So these are the places at which somehow I assume I already have a measurement of signal to noise ratio. Of course, in practice, it would be more random, but just for the example, I put it uniform here. Now, if you want to reconstruct the rest of the radio map from those initial training samples, there are different ways you can do that, but there are two main ways. One way is to just use an image processing perspective on that problem. Basically, this is an image that contains a number of pixels of different colors, and I just want to reconstruct the colors at the missing pixels. And I completely ignore the fact that this is actually something from a wireless problem with a robot, and these are SNR measurements. I ignore all of that. I just say this is an image. Right, so you can do that. You can use, for example, the algorithms such as k-nearest neighbor directly apply to this SNR domain image. Another approach is to use your expert knowledge as a wireless communication engineer and leverage the fact that you know that these colors are not just arbitrary colors. They are coming from RSSI values that in fact follow a certain structure. They are following a certain model. We might not know the coefficient of the model, but we know there's a model and we understand well enough the model, just like the one I presented a few seconds ago. And then what you'll do is that instead of doing classification just based on the image, you will do based or in the domain of the propagation classes. And that's the only thing you need to do classification over. Once you know in which propagation class you are, you'll be able to learn the model coefficients, and you'll be able to reproduce the radio map. This picture is basically showing you that, as can be predicted, if the channel models are good, then it is good to leverage that knowledge. And this shows the root mean square error of the reconstruction for different training sample size. As you can see here, the method that using the knowledge of the child model is actually better at reconstructing the image. Of course, if you don't have any model for propagation, then it's another story. Maybe we can discuss that at the very end. We have some ideas on that as well. All right, these are just, this is not an experiment so far, by the way, these are just MATLAB experiments. And it shows the effect of having more or less training data samples initially. So of course, if you have more, you can reconstruct the radio map more precisely. And if you have less, then you have a more coarse approximation, which may or may not be good enough, by the way, because the point is not to have a precise map. The point is to put the robot at the right place. That's the only thing you care about, which in this case happens to be that point here. Okay, I want a small digression to indicate that reconstructing a radio map can be nice. I mean, it's a fun thing to do, but it is not a solution that scales very well. Imagine that you have to position a robot that serves as a wireless relay for 1,000 users deployed in the city. In principle, you have a different radio map for each one of these users. So obviously, you're not going to run 1,000 radio map reconstructions algorithms in parallel because that's just too intensive. So you need to wonder, what is it that correlates all these radio maps together? Well, if two users are close by in the street, probably their radio map is going to be quite similar because they are surrounded by the same buildings. So what correlates everything is the shape and position and height of all the buildings. So this is really what matters. So the next question is, can you use the measurements, the same measurements, these RSSI or SNR measurements, to directly reconstruct this physical map? And from the physical map, then you can reconstruct the radio map for any number of users in a scalable manner. The answer is yes, you can do that, in fact, and this is fairly simple. This is similar to trying to reconstruct the shape of an object in 3 dimensions when that object is being exposed to a number of different sources of light. And just looking at the shadow information, if you have, for example, 3 shadow information, you can reconstruct the shape of the object. Well, this is similar here. If you have a drone flying in the sky and a number of users in the streets, for each one of the users, you make a measurement, an SLR measurement. And if you can manage to classify that measurement as being line of sight or no line of sight, you will infer whether there is a building along the way or not. You may not infer the height of the building immediately, but if you have enough measurements, at some point, you will also infer the height of all the buildings. So this is an example of, again, a MATLAB experiment. This is a true virtualized city, and you have a drone flying at an altitude of 800 meters along an arbitrary trajectory, which is a square here. And then this is the map that you reconstruct using just the RSSI levels alone from 1,500 users that are scattered across the city. You can also optimize different things. You can optimize the altitude of the UAV. Turns out that if you fly too high in the sky, then most of the links are going to be line of sight links, and you won't learn very much about the shape of the buildings. And if you fly too low, most of the links are going to be non-line of sight, and again, you will not learn too much about the city. So there's an optimum altitude that you can derive in closed form. We've done that a couple of years ago. Okay. You can also exploit the fact that the radio maps and the physical maps are interrelated through the channel models. Once you have understood that idea, you can come up with better algorithms that are going to cycle through radio map estimation and physical map estimation, like iteratively. And it turns out that this will also improve performance. Okay, we call it joint 3D and radio map reconstruction. But let me move on a little bit. So what I've talked about so far now is been how if you get an initial set of radio level measurements that are done at arbitrary measurement locations, then in principle you can reconstruct radio map or physical map. Let's suppose that this has been done. So now you have the radio map. So in principle, you know in advance for any point in the sky how good the channel is going to be between the UAV and any user on the ground. Let's suppose that this has been done. Now the question is, where should you put the UAV and what path should it follow? Okay, so I will talk about three main use cases. The first one is UAV serving as a cellular relay. So there is a base station not too far away that the UAV can connect to, most likely in line of sight, as what was mentioned this morning. And then the UAV serves as a relay down to some users. The second scenario is a scenario where the UAV is basically alone. There's no base station. It is a flying base station by itself, and the goal is to collect IoT data as quickly as possible, given you have a fixed energy constraint. The third one is UAV serving as an extra flying router or relay node in a peer-to-peer network or in a mesh network. So you have a number of people on the ground. You would like to guarantee a good peer-to-peer connectivity between any two pair of ground users. Where should the robot be in that case? So we've designed algorithms for these problems, but we've also constructed experiments. This is what I think I wanted to show you also today. Now, there's a common theme and a common challenge behind all of these problems, which is that rich information can easily be too rich information or too much information. As I mentioned before, you know, the kind of maps you want to use for your optimization is highly irregular. So how do you design an optimization algorithm that still can exploit the essence of that information without getting stuck in a ton of local minima? Okay, so let me pass on something. So I'm going to explain our ideas there, but I also want to show you the experiment a little bit here. Let me get rid of the sound because it's annoying. Okay, so this is an experiment we've done now 2 years ago at Eurocom, and this is the cellular relay experiment. First of all, you see the kind of robots we're building in the lab here. This is very similar to what the Lakeside lab people have shown this morning. Here's the quadcopter. And what you see under the quadcopter here is actually a full-fledged 4G eNode B. We hope to upgrade to 5G eNode B very, very soon. And this eNode B, okay, it has the full LTE protocol stack running. This is based on the open interface, open source implementation of 4G. And now we can put 5G in it. It is operational. And this flying base station is flying in the air, and then we'll connect to a fixed base station that you can see here is hidden behind the wall, but it's actually on the roof of our building here. And then the UAV will act as a relay to serve this user here, which is going to move around. So let me see if I can manage to make it work. Yeah. Okay, so this is the picture of our base station. The user is here. So without the UAV, we measure the throughput. You see we have about 3.8, 3.5 megabit per second, up to 4 megabit per second downlink. And then we let the robot fly. This is an autonomous robot. So there is a machine learning algorithm that is implemented in the robot that lets it figure out where it should be to provide the best possible service to this ground user as the ground user is going to move around. You see that with the robot, you get better throughput. This is more like a functional test. I mean, I'm not claiming that a UAV always gives you 50% extra throughput, but it's just to show that it works. And then more interestingly, I think, is the adaptability of the system when the ground user is moving around, how the UAV can sense that he also has to move in order to maintain the best possible channel condition to both the base station and also to the ground user, because it's a relay, it has to maintain good quality on both. And what you see here down below is a picture of the algorithm running in the drone, where the purple dot is the next predicted optimal place to be. Okay. All right. And by the way, so the robot here makes use of this map of the environment in order to make the channel prediction. Okay, in the second scenario, so by the way, in the first scenario, the map is quite simple because this is a campus environment. So we didn't need to resort to any special tricks. But in principle, when you have a complex environment, the map can be quite a complex object to deal with. So you need to come up with a clever solution to avoid this non-differentiability problem. So this is what we'll see now in the second scenario, which is the IoT data harvesting. So in this scenario, the problem is the following. You have a number of nodes on the ground, which could be like smart city sensors, for example, and they are loaded with data, and this data has to be uploaded to the drone as quickly as possible. So the UAV is trying to optimize its trajectory in order to harvest all the data as quickly as possible from all the sensors. So this can be expressed by an optimization problem, which is like this. It's a max spin problem because you want to maximize the amount of data you are able to harvest from the worst case sensor. This is why you have a mean here. Okay, in order to preserve some form of fairness or balance between the sensors. Otherwise, you could easily ignore some sensors and never going to harvest their data and just focus on the good ones. But we don't want to do that. We want to have data from everywhere. Oops, sorry. And then subject to what? Well, subject to, you need to have a trajectory. And then the trajectory, by the way, is expressed by the variables x and z. Z is the altitude, x is the two-dimensional trajectory. And then q is a set of basically scheduling variables, because we don't want to have interference between the sensors, so we let them talk one at a time. So there's a sort of a TDMA priority rule here, and this is what is expressed by the scheduling constraints, like no more than one sensor speaking at a time. Now, CK is the capacity, so in the Shannon sense, so it looks like this formula that you see here. Now the problem is that in the Shannon sense, you have the SNR between the UAV and the nodes, and the SNR very much depends on whether you are in line of sight or non-line of sight condition, right? Because the path loss is not the same. So of course you could try to inject the map in there, but then very quickly this problem becomes untractable. So you need to come up with another solution. So what we did is that we looked at the following idea, which we call map compression. The idea is to be able to capture the main value of those maps without having the non-differentiability issue that comes with the original map. So the way you do that is that in fact, you create a model that's a little bit halfway between the probabilistic model, the one I showed in the beginning, and the purely map-based model. So the way we do it is that we create a local probabilistic model, which is aided by the map. So the form it takes is this. It takes the same shape as the classical line of sight probability model that many of you may have seen, or at least if you have been doing some UAV work. Except that here in the parameters A and B, I'm going to put a dependency on which user I'm talking about. And this is very important because, for example, if you have a user that's located in the middle of, let's say, Central Park in New York City, it's not the same as if the user is located elsewhere in Manhattan, because elsewhere in Manhattan, you're surrounded by tall buildings, and if you want to maintain line of sight to that user, you better be super close to that user. While if the user is in Central Park, you can actually be very close to the user located elsewhere, like close to the buildings, and you can still maintain line of sight to that particular user. You don't have to be close to that user. So that kind of information is indeed captured by the map, but we just capture the essence of it through this probabilistic model that is made user dependent or user location dependent. Okay. Well, with this idea in mind, you basically rewrite the optimization problem, and I will skip the details, and then you end up with a problem that can be solved by a family of algorithms called successive convex approximations that are basically classical tools from optimization. Okay, so this is an application of this concept, and this is a scenario that was actually experimental again on the Eurocon campus, same buildings as what you saw before. This is an IoT data harvesting scenario. There are 3 IoT sensors, N1, N2, and 3. I have my robot here in a red circle, and I'm going to load my data buffers with data, and my goal is to empty those buffers as quickly as possible. And I want to compare that with a case where the trajectory is not optimized. So the way I do this is that I will compare with the case where the trajectory is just a circle, and the size of the circle is the same as the size of the optimal trajectory. Okay, so I have a fixed energy limit, and that's it. So let's take a look. All right, so this is loading the data, and now the drone is taking off and starts harvest the data from those laptops. And you see the state of the buffers as the UAV is autonomously moving around the sensors and kind of sucking up all the data that is loaded there. Note that the scheduling algorithm used in both cases is the same. Okay, the scheduling algorithm has to do with whichever sensor you're closer to, that's the one you're going to harvest from. Okay, I think I'm going to skip the rest, but the basic idea is that if you can optimize the trajectory using this learning algorithm, then you'll be more efficient in harvesting the IoT data compared to a random trajectory, let's say, of the same total flying time. Okay, should I? Maybe you won't believe me if I don't stay until the very end, but I can tell you that on the left-hand side, the buffers is going to be empty first. Okay, I think you're convinced by now. Let me move on. All right, third scenario, maybe of interest to some of you guys. This is the mesh connectivity scenario. Could be useful in a situation where you have maybe a disaster and then you have a squad of fire brigades, law enforcement, or whatever, rescue people. And could be also military personnel in a war scenario. Basically, you want those people to be able to connect with enough data rate reliably between themselves. There's no infrastructure, so you rely on mesh connectivity. So mesh connectivity means that in some cases, you connect directly between the peers. In some cases, you have to relay through one of the peers, right? So this is the result of the routing algorithm. a little bit like in an ad hoc scenario. And now the opportunity is to inject a robot at some place above, and then which is offering the opportunity to act as a relay when needed. It doesn't have to be always used. I mean, if two users are close together, they won't go through the robot, clearly, they won't meet. But if you want to connect to another peer that is the other side of the city, then maybe you connect through the robot. So this is up to the routing algorithm to decide. So now the question is, given that we don't really control the routing algorithm, where should the robot be? You know, and adapt as the people on the ground are moving around. How should the robot behave? So it turns out this again can be formulated as an optimization problem. So I have to say that in the beginning, when we dealt with that problem, it was pretty hard to understand what to do with routing, because obviously the optimal path, or should I say the optimal placement algorithm, depends on the routing. But I don't have any closed form expression for the routing solution. I don't know what it's doing. It's fairly complicated. So we had to use a model for the routing algorithm. And the model we used was the following. And this is something that is a close approximation to what's going on in practice in mesh networks, which is the following. If two nodes are close together and want to communicate, they probably will do it in a direct hop. If not, what would probably happen is that the nodes will go through a relay. One of the extra nodes in the network will serve as a relay. So essentially, you have this picture where all the nodes that are very close together can be clustered together, and we decide that whatever communication inside the cluster will take place without the robot, just directly. And if a node that belongs to one cluster needs to communicate to another cluster, it will go through the robot most likely. So this is how we model the routing algorithm. It is an approximation. And based on that, we are able to come up with a closed form, at least mathematically optimizable problem. It's still a max-min problem because you want to make sure that every possible pair of ground users has a good enough connectivity. So that's why you have a max-min scenario. CK is again a rate or capacity for link K. And then we use the classical Shannon expression there. And again, this rate very much depends on whether there's line of sight or not between the nodes, which you would know because you have the map, but it's very hard to inject the map in there and keep the problem differentiable. So again, we use the map compression algorithm there. And let's see what I use. I'm going to actually skip this one, but if you're interested, I send you the video. It's also available on YouTube. But basically, we did an experiment with a bunch of nodes on the ground, and then we let them move, and we saw how the robot moves around to be at the optimal relay location for this mesh network at any time. Okay, I want to tell you a little bit about the last part of my presentation, which is, like I say, a twist over the first set of problems.
So David,
what is the twist I'm talking about?
David? David?
The twist is to say, in everything I've done so far, I have broken down my problem in two parts. In the first part, I have acquired some initial measurements by flying the robot at arbitrary locations. I obtain RSSI values, let's say. And then as a second part, I use those values in a machine learning algorithm to infer my optimal solution, which could be my optimal placement, or I will show you later optimal location estimates, well, different things you want to do with your robot. However, in practice, the training part is actually expensive when you deal with real robots. And you might not have the time to fly the robot around at will to collect training data. So there comes the interesting following problem, which is, suppose that I give you, let's say, only half an hour of training data collection. What is the path that the robot should follow during this half an hour to collect the measurements which are as informative as possible towards the problem you want to solve? This problem is a classical problem in robotics called active learning, which you can transpose to our setting here. For example, suppose that the goal of the robot is to reconstruct a 3D physical map of the environment. It's initially you have no information, nothing. You lift off, you're going to collect measurements, and very quickly you would like to reconstruct the map, the best possible map that you can by flying at the places that give you the best possible information about the map you want to reconstruct eventually. How do you do this? So this can be done. This can be done by optimizing the trajectory, which this time is a learning trajectory, discretizing the position of the robot in a discrete graph that represent different discrete positions, and then the trajectory is now represented by a path over a discrete graph. This is what is represented here by the small graph. And then every move you make between 2 points on a trajectory is basically going from one node in the graph to another node in the graph. And the idea is that it's possible to assign labels to each one of those edges in the graph, corresponding to how much information is being collected over that edge about the problem you want to solve. So if you want to estimate the city map, the edge will indicate how much information you collect along this edge about the city map. Okay? And this can be done by using metrics such as Fisher information that take into account the distribution of the data you're collecting. Typically, when you want to reconstruct the city map, an implicit goal of the robot is going to be to balance the number of line of sight and non-line of sight measurements it's collecting. I mean, this is what we've seen is something that is fairly important to do. So the robot is flying a path that kind of follow that goal. I mean, this is an after the fact interpretation. This is not an explicit criterion we use. And this is, for example, the kind of trajectory that happens to be optimized. So instead of flying in a square, don't do that. Fly this strange shape that takes into account the position of the buildings that the robot is detecting initially and is relying on to update its following steps in the path. And this does better than any possible other arbitrary path that we tried at random. Okay, so this is, by the way, this is implemented by dynamic programming, which are kind of computationally intensive programs, but at least on paper is possible to do. The second example that we looked at is how can the robot learn about the channel as quickly as possible? What is the path that it should follow to estimate the channel model coefficients as quickly as possible? And there again, we obtain this kind of trajectory here. Definitely not straight line types of trajectory. And also in terms of altitude, you see the robot is trying to experience different altitudes in order to enrich its data sets. Again, this problem has been solved using dynamic programming here. Okay, in my title, I talked about user localization, so I think I should say something about this. This is an important goal in 5G, but also in 6G, try to get efficient localization algorithms. So there, what we try to do is to see if the robot, just by collecting RSSI measurements, so signal level measurements, whether the robot is able to localize users or not. So if you look at the localization literature, typically RSSI measurements is not considered to be a reliable source of information to obtain localization results. And that's because RSSI measurements are typically noisy. And the relation that you have between RSSI to a location depends on a channel model that you don't really control entirely. I mean, we have good channel models, but I mean, they may not be super realistic, super precise. So that's the drawback of these RSSI-based localization. Of course, this conclusion was mainly drawn when you try to do localization using RSSI in fixed networks, using, for example, RSSI collected from fixed base stations. But if you do that with a UAV, you get a completely different picture because the UAV, first of all, can move around in 3D. So you get a lot more measurements that are super rich. And the second part is you can optimize the path itself to give you the most informative measurements about your localization problem. So this is not something you could do with fixed infrastructure. So there you go. Here's a problem. You want to collect RSSI measurements from let's say, K users, and you don't know the channel model parameters initially. So you want to learn channel model parameters and localize the users. And possibly you have a 3D map of the environment. If not, this is something you have to also estimate on the fly. Okay, in the example I'm going to show, I will assume that you do have a 3D map of the environment. There we use a combination of particle swarm optimization. I mean, the whole thing is not standard convex optimization. So that's why you have to resort to slightly, off the beaten tracks optimization frameworks like PSO. And then we're going to do again this active learning, because I want to find a way to say localize the users as good as possible within, let's say, 10 minutes of flying time, no more. And again, we resort to this Fisher information type of metric to guide the robot along the best possible path. Okay, I realize I don't have a slide to give you the details on the algorithms, but the details are in this paper that was recently accepted, so in IEEE IoT journal. But I want to show you an experiment. So this is not, sorry, this is not a live experiment. This is a MATLAB experiment. We're still working on the live experiment. I guess what you're going to see here is the UAV starting here at some arbitrary location. The UAV is only going to rely on RSSI measurements to localize the user. There's one user that is here. And this little square here indicates the initial guess done by the UAV. So initially, the UAV has no clue where the user could be, so we take an arbitrary guess. And this curve will show the evolution of the localization error as the robot is flying in the air. All right, let's see if this works. So initially, the trajectory is going to look a little bit random, but fairly quickly, from the initial measurements, the robot gets a better idea of where the user can be. And it turns out that a very good way to localize the user from RSSI measurement is actually to fly towards that user. So this is what the UAV is doing here. Okay, so quickly you see that it's really hovering along the way. The reason why it diverged at the end probably is because we put a fixed destination point, so that the robot has to fly back to a home base station, which was somewhere in the cell. All right. I think I've spoken long enough, probably. I want to say, just to give you a few perspectives. So UAV-aided networks, I fully agree with the previous speakers, it's something very promising. To make the network very flexible, and also bringing the content much closer to the end user. People are also considering caching applications with UAVs. I don't know if it's super realistic, but in principle, you could upload movies in the UAVs and then download those movies when you're close to the end users. Something that is interesting to look at further, I think we started here, but a lot remains to be done, is more interactions between the communication models and the robotics model. So the mapping is something very important there, but we can go a bit more beyond. I will mention it in a second. You can do a lot of stuff with the UAV, not just acting as a relay, but also you can localize users. And I didn't mention that, but a very important scenario of UAVs is also the flying terminal scenario, where, let's say you want to deliver some goods from A to B, and you need to reliably communicate with the user for control purposes all along the way. This is a very hard problem, as it was shown this morning, because of the cellular interference that you have that makes the problem challenging. So something we looked at, again, using the same mapping ideas that I mentioned here, is how you can alter slightly the mission trajectory, which, if you're delivering some goods, might be a simple straight line. If you alter that a little bit, move a little bit off that straight line in order to accommodate the constraints for reliable connectivity. It's a very powerful concept that does require some learning and some optimization, but you can show that by slightly deviating from the original mission trajectory, you can get much better guarantees for connectivity. Okay, lots of hard problems for the PhD students in the room, which are the majority of people here. I presented results with just one UAV, but of course it's interesting to see how multiple UAVs could coordinate to achieve similar goals. Low complexity algorithms, especially for the active learning part, is something where we have not been able to really experiment live there, mostly doing MATLAB experiments, because dynamic programming is a very complex tool. I ignore completely the RF issues, but it was shown this morning that a simple problem, which is how to pick the right antenna on the UAV, is actually quite challenging, because the UAV is moving around, there's lots of vibration, there's lots of interactions with the propellers that tend to affect the channel propagation. So picking the right antenna model and pattern is a very challenging problem and very interesting one. Another interesting question is, where should computation take place? In the experiments, I've showed you computation sometimes takes place in the robot, sometimes it takes place on the PC that is on the rooftop, and then we upload the optimal trajectories to the robot. But most cases we have implemented inside the robot. So it's an interesting trade-off. If you implement off-board, could be nice because you have more computing resources. But then if you have intermittent communication to the robot, it can be a challenge because it's not very reliable. And the last point I want to mention is something where something very interesting to do is to fuse or combine radio data and more classical vision, radar, LiDAR data. Why? In fact, you saw the use cases this morning. We're mainly mentioning missions where the robot is capturing some video data and trying to use that for rescue and detection purposes. What I showed today is that, in fact, you can do many things with just radio data. But combining the two is actually something that makes sense in many cases. Why is that? Because radio data, vision data, by nature is very informative about your immediate surroundings. You see the buildings, you have the right in front of you, and you have a very clear view of that building, right? And if there's a user down there, you might also see it. But if it's beyond the visual line of sight, vision data by nature doesn't give you any information. So it's very precise and rich in the short range, but very imprecise and vague in the long range. The radio data is kind of the opposite. Radio data is very powerful to give you information that crosses beyond buildings, because by nature, there's the capability of radio waves to go through buildings. So you get a picture, a very complete picture that goes much beyond the visual line of sight. However, the radio data is by nature very noisy and following models that are very complex and that we don't fully understand. So they are very complementary. So what we've done, in fact, a few months ago, is try to see how you combine those properties together and come up with the best detection algorithms. Okay, I think I'll stop here. That way we leave quite some time for questions, and thank you very much for the attention. Thank you.
So thank you, David. So do we have any questions from the audience or comments for David? Of buildings, where you had one example where you used, was it 1,500 phones or user terminals, that of course in MATLAB, but I was wondering, in a practical scenario, would you need to somehow calibrate these phones or the expected power levels before you can actually use the data? Because I suppose if someone has his phone in the pocket or in a backpack or however it's rotated, it can have an impact on the signal strength.
Yeah, I completely agree with you, and that would be the gap between a MATLAB experiment and a real one. And I would add also other problems. Typically, the phones sometimes at least use power control, and so the power may not be even the same. It might be quite different from what you think. So for power control, you will need to go to a certain slices of service for which you know that power control is not being applied, that power control is going at full power. And then remains what you're talking about, which is problem of orientation and local shadowing. But I think this would be just added to the overall shadow noise that we anyway consider. Like if you look at our model, there's a fair amount of shadow noise in there. And this is compensated by the fact that indeed you have a lot of measurements, so it tends to average out. But for sure, you're never going to get a super precise localization with just radio because of the problems you mentioned. But for reconstructing the CD, if you have enough such measurements, it would be good enough because it can average out.
Okay. So, any questions from anyone?
One question. Thank you for presentation. I was wondering how accurate was the user localization in meters?
What, sorry?
How accurate was the user localization? The mean squared error that you reached and show us this. Was it in the rate of tens of meters?
No, it's less, because if you remember, the curve was shooting down almost there at lowest level. So, and this is 100 meters root mean square error. So it's probably in the meter range.
Okay. And
like we said with Jimmy, this is a MATLAB experiment. So.
And it only used the received signal power and nothing else. Like.
That's right.
Okay, thank you.
Well, I was also wondering a little bit, when you created these 3D maps, where you found out that the optimal trajectory was not straight lines, but something like zigzagging across buildings and up and down. I was just wondering if there's any intuition behind the optimal movements when you consider.
Like, for example, this one, I try to explain, but I mean, this only goes so much. I mean, the thing we understood was that, for example, in the case where the goal is to quickly learn the propagational model parameters, then one of the objectives of the robot is to balance the number of line of sight and non-line of sight measurements. So it will look for a trajectory that makes it exposed to an almost equal number of line of sight and non-line of sight opportunities. So in this case, the drone knows the maps in advance. It knows the building maps, so that's why you can use that to create such opportunities.
Okay. Yes. And the flying distance was fixed, right? So it tries to find the best trajectory.
Yeah. The total flying time is fixed in advance. That's right.
Yeah. Okay. Thanks. So we still have a bit of time for questions.
Yeah.
Yes.
I also have a question about the localization. Did you use uplink signal or downlink signal for user location?
Okay, so because it's a MATLAB experiment, I'm pretty sure it does not matter. I don't actually remember. I believe it must be uplink signals in this particular case. I don't know if Omid, my student, is here and listening, but I guess not because he knows this word. I guess it's uplink, but it doesn't matter in a MATLAB experiment.
I think about the rate. Did you use how do you actually optimize the trajectory?
I'm sorry, I didn't understand the question.
I mean, what metrics that you use for the trajectory?
Yeah, like I said, it's similar to this problem here. So you discretize the set of trajectories as being moves over a discrete graph, and then you try to at every step along the way you try to take the move along the next neighboring nodes that maximizes the Fisher information. The Fisher information is an information metric that takes into account everything you know so far, and then looks at the amount of innovative information you're going to get by following either this path or that path or that path. And then you take the one that maximizes the amount of fresh information you have about reconstructing, here in this case, reconstructing the city map.
Yeah, so you didn't use any communication metric for the trajectory. So I mean, it should be the uplink. Your signal that you is uplink. If it's downlink, maybe some metric from the UAV is also important. For example,
yeah, you're right, and then it will, if it's first of all, if it's downlink, you would need to collect those measurements back to the drone. So either it's a TDD system. If it's not, then you need to rely on feedback. That sounds a bit complicated. So most likely uplink.
Okay, thanks. Thanks.
Hey, Konstantinos.
Oh, we don't hear you.
No, still not.
So you're not muted, but there's no sound.
Usually is when you plug those headsets, they tend to disconnect the audio system. I have lots of bad experience with that.
I just did that. Can you hear me now?
Yes, yes.
Yeah.
Okay, excellent. So very nice talk, many things here. I just wanted to ask a few things about the live demo you did, because I didn't pay too much attention there. So you have a flying UAV acting as a relay, right?
Yeah, we have these three scenarios. I don't know which one you had a question on.
Yeah, no, I guess the first one. So yeah, you showed the picture. Yeah, here. This one. All right. So the UAV actually does both, connects both to some UE, right, using 4G, and then what does it use to connect to the base station? Also 4G or something.
So when we did this experiment, which was close to 2 years ago, the 5G version of Open Interface was not ready. So it is definitely 4G. And then in fact, the trick is in this case to act as a base station relay, is that this carries both a base station that is used to communicate to the ground user, and it also carries a client like a UE to communicate to the home base station. that way you can communicate to both at the same time.
Okay, okay, I see. And is there any indication of you know, how long the UAV could last in terms of you know, it was hovering also, or was it stationed? I mean, how long was, let's say, the hovering time, you know, while it was serving on both directions?
You're talking about the battery life here?
Yeah.
These models here, they can stay in the air up to 20 minutes, no more.
Okay, that's fair enough. All right, thanks. I'm sure we'll have more probably to discuss in the panel coming up. So anyway.
Thank you,
Thanks a lot.
Konstantinos.
So just a follow-up for this experiment. So the model of the environment, that was simply these two square blocks or cubes of the buildings. So very simplistic model, actually.
Yeah, so you mean, for example, it did not capture like this terrain, like this hill that you see here, that was not captured in there. We didn't capture this block behind because where the user was located was not necessary. And indeed, it is simple, but simple enough.
Yeah, okay. So you, yeah, I suppose even if you had a more, let's say, detailed building, you would just need to have like an outer boundary of that building to make sure that that you are not in a non-line of sight situation.
Yeah, exactly. This is the critical information is to predict where you're going to be in line of sight or non line of sight, which doesn't mean, by the way, that the UAV necessarily wants always to be in line of sight, but it's a choice it has to be aware of, because sometimes you can be, you know, non-line of sight to one of the objects, but if you're close enough, it's still okay. So it depends, but definitely you need to be aware of that.
So have you experienced any problems with being in between lobes, like we saw in the Lakeside Labs results?
Yes, we experience lots of problems related to maintaining a steady connectivity performance. Indeed, we found that things tend to change quite a lot. Like when you move the UAV by a couple of meters, sometimes it changes completely the signal level. Even if you stay in non-line of sight zone, or if you stay within the line of sight zone, you still have a lot of variability. But we did not trace it back to a particular reason, such as being in that lobe or that lobe of the base station.
Okay. Any other questions from the audience? No? Then I will.
No, I just wanted to say, like, for people interested in machine learning, the next step we're looking into these days is the use of reinforcement learning in order to deal with the case where you have very little prior information. And that's interesting, but that's quite challenging also, because you have to learn everything on the fly.
Okay. So thank you very much for your lecture, David.
Okay, welcome everybody. And if people have questions, they can always email me. I'll be happy to interact over email.